Hello there, and welcome to Sleepy Science Vault. Somewhere out among the stars, in the quiet dark between galaxies, there exists a boundary unlike anything else in the universe, a line that, once crossed, can never be uncrossed. Tonight, we're going to explore that boundary. Slowly. Carefully. The way it deserves to be explored. Black holes have fascinated scientists and dreamers alike for over a century. They bend the rules of space and time in ways that still challenge our deepest understanding of physics. But at the heart of every black hole lies something both simple and profound, a threshold known as the event horizon. It's the feature that gives black holes their name, their mystery, and their quiet, inescapable pull on the human imagination. Over the next several hours, we'll drift through 100 facts about this strange and beautiful boundary. Not to overwhelm you with information, but to let each idea settle gently into your mind, one at a time, the way starlight settles onto a dark field on a clear night. There's no need to remember every detail. Just let the facts wash over you, like a slow tide moving across still water. Let's begin where the mystery truly starts, at the edge itself. The event horizon is often described as a one-way boundary. Once something crosses it, whether that something is a spacecraft, a wandering asteroid, or even a single photon of light, there is no return. No signal, no message, no flicker of information can make its way back out to an observer watching from a safe distance. It isn't that escape is difficult. It isn't that escape is expensive, in terms of fuel or energy. It's that escape becomes, in a very real and mathematical sense, impossible. This is part of what makes the event horizon so different from anything else we encounter in daily life. We're used to boundaries we can push against, walls we can knock on, doors we can, with enough effort, force open. But the event horizon offers no such negotiation. It simply closes behind you, silently, and the universe you once knew continues on without you, forever out of reach. Researchers often describe this region in a particularly evocative way. They say that even light itself becomes trapped here. Light, which under almost any other circumstance is the fastest and most unstoppable thing in the universe, finds itself doomed, unable to climb back out once it strays too close. This is precisely why the event horizon has earned its now famous nickname, the point of no return. Think about that for a moment. Light. The very thing that lets us see galaxies billions of years in the past. The thing that carries information across the vast emptiness of space at the fastest speed nature allows. Even light cannot escape from within this boundary. Not because it slows down. Not because something physically blocks it. But because the space itself, the very fabric that light travels through, has been so profoundly warped that every path, every possible direction, leads only deeper inward. To understand why this happens, scientists often speak in terms of escape velocity. This is a concept you may already be familiar with from Earth's own gravity. Escape velocity is simply the speed something needs to reach in order to break free from a gravitational pull and continue on forever, rather than falling back down. For Earth, that speed is a little over 11 kilometers per second. Fast, but achievable. Rockets do it every year. But near a black hole, something extraordinary happens. As you approach the event horizon, the escape velocity required keeps climbing and climbing, until, right at that boundary, the escape velocity becomes equal to the speed of light itself. Beyond that point, the escape velocity would need to exceed the speed of light entirely. And since nothing with mass, and not even light itself, can travel faster than light, escape becomes fundamentally, permanently impossible. This is one of the clearest and most elegant ways to understand what the event horizon actually represents. It is the precise boundary, drawn by gravity itself, where the required escape speed crosses over the ultimate cosmic speed limit. Now, here's something that might surprise you. Even though nothing can escape from within the horizon, light itself doesn't slow down there. Locally, right at that boundary, light continues moving at its usual, familiar speed, the same speed it moves anywhere else in the universe. What changes isn't the speed of light. What changes is the geometry of space itself. Space becomes so curved, so profoundly warped by the black hole's gravity, that even light moving outward at full speed finds every possible path curving back inward. It's not that light is being slowed or stopped. It's that the destination it's trying to reach, the wider universe, has been geometrically removed from its future. This distinction matters more than it might seem. It shifts our understanding away from thinking of the event horizon as some kind of sticky trap, and towards something far stranger and more elegant, a boundary written into the shape of space and time itself. Which brings us to a deeper truth. The event horizon is not a physical surface. It has no atoms. No solid material. Nothing you could reach out and press your hand against. Unlike the surface of a planet, or the outer layer of a star, the event horizon has no substance at all. It is, instead, a geometric boundary, a mathematical line drawn into the structure of space-time, marking the place where escape transitions from difficult to impossible. This is worth sitting with for a moment. When we imagine black holes, our minds often reach for familiar images. A dark sphere. A void with edges. Something solid, lurking in the blackness. But the event horizon defies that instinct entirely. It is the true boundary of a black hole, yet it is not a visible surface. Not a shell, not a wall made of any kind of matter whatsoever. It's simply the outer edge of a mathematical region, one defined entirely by where light and matter can, and cannot, travel. Scientists sometimes describe it this way: the event horizon is the outer boundary of the region from which no future path leads back out to the wider universe. Every possible trajectory, every conceivable route through space and time, once inside that boundary, curves only inward. There is no direction you could choose, no maneuver, no burst of speed, that leads back outward again. All roads, in a very real sense, lead only deeper into the black hole. And this isn't limited to physical objects like spacecraft or stars. Nothing inside the event horizon can send any kind of signal back out. Not light. Not radio waves. Not gravitational ripples. Not the faintest whisper of information. Once something crosses that boundary, it is, from the perspective of the outside universe, gone. Silent. sealed away behind a threshold that cannot be breached in either direction. It's a strange kind of finality, one that exists nowhere else in nature. And because the horizon has no material substance, it also has no solid edge you could stand on, or touch, or even measure directly with your hands. There's no clanging metal boundary. No shimmering wall of energy. If you were to fall toward a sufficiently large black hole, you might cross the event horizon without feeling a single dramatic jolt, without any local sign that you had just passed the point of no return. The boundary is defined not by anything physically present at that location, but by the future paths available to you from that point onward. This leads us to perhaps the most conceptually delicate idea of all. The event horizon is what scientists call a global boundary. Its definition doesn't depend on what's happening locally, in the immediate area around you. It depends on the entire future of space-time itself. In other words, to know exactly where the event horizon lies, you would technically need to understand how space-time evolves, forever, into the infinite future. This is deeply different from how we normally think about location. We tend to imagine boundaries as things you could mark on a map, fixed points you could identify just by looking around. But the event horizon isn't like that. Its position is tied to the ultimate fate of every possible path through space-time, an idea so vast, so far-reaching, that it stretches the very definition of what a boundary even means. It's a humbling thought, isn't it, that something so quietly decisive, so absolute in its finality, is defined not by a place, but by an entire destiny written into the fabric of the cosmos. As we continue through this journey together, we'll explore how this remarkable boundary was first predicted, long before anyone had direct evidence that black holes were real. We'll drift through the mathematics that first hinted at their existence, the observations that eventually confirmed them, and the strange, almost dreamlike physics that governs everything from the curvature of light bending around them, to the way time itself begins to behave differently as you draw near. For now, simply let this first idea settle, that somewhere out there, scattered across the universe, exist boundaries drawn not from matter, but from geometry itself. Places where light bends beyond return, and where the ordinary rules of escape quietly, and permanently, come to an end. In our next set of facts, we'll continue drifting closer, exploring how this boundary came to be understood, and what it reveals about the outer edges of some of the most extreme objects in the universe. For now, let the darkness settle comfortably around you, and let your mind rest in the quiet vastness of space. We left off with the idea that the event horizon is not fixed to any single place, but tied instead to the entire future of space-time itself. Let's carry that thought forward now, because it opens the door to understanding just how varied, and how individual, these boundaries truly are. Every black hole has its own event horizon, and no two are quite alike. The exact location, the exact shape, the exact size of this boundary depends entirely on the properties of the black hole that creates it. Chief among these properties are two simple but powerful characteristics: mass and spin. Together, they shape the horizon in ways that reveal just how personal, in a strange cosmic sense, each black hole really is. Let's start with mass, since it's the easier of the two to picture. The more massive a black hole is, the larger its event horizon becomes. This might seem intuitive, almost obvious, but it's worth pausing on, because the relationship is remarkably direct. Double the mass of a black hole, and you double the radius of its horizon. There's an elegant simplicity to this. A black hole that contains the mass of 10 suns will have a modest horizon, tucked away in a relatively small region of space. But a supermassive black hole, one containing the mass of millions or even billions of suns, stretches its horizon out to a scale that dwarfs entire solar systems. It's a strange thing to imagine, a boundary, invisible and intangible, expanding outward simply because more matter has fallen into the darkness at its center. The horizon isn't just a marker of where escape becomes impossible. It's also, in its own quiet way, a record of just how much the black hole has consumed and grown over time. Now, mass alone doesn't tell the whole story. There's a second factor at play, one that adds a layer of complexity and beauty to the shape of these boundaries: spin. Not every black hole spins. Some are calm, still, rotating so slowly that for all practical purposes, they can be treated as perfectly at rest. These are the simplest black holes to describe, at least mathematically. For a black hole with no rotation, the event horizon takes on the most elegant shape imaginable, a perfect sphere. Smooth. Symmetric. The same distance from the center in every direction you could measure. But many black holes do spin. And when they do, everything changes. A spinning black hole doesn't just rotate in place, the way a planet or a star might. Instead, its rotation drags the very fabric of space-time around with it, twisting the space near the black hole into a kind of cosmic whirlpool. This effect has a name, frame dragging, and it means that near a rotating black hole, space itself is being pulled along, swept into motion, whether or not anything physical is there to be moved. Because of this dragging effect, the event horizon of a rotating black hole is no longer a simple sphere. It becomes distorted, flattened slightly at the poles, and bulging outward around its equator, not unlike the way a rapidly spinning planet bulges very slightly at its middle, though the effect here is far more extreme, and far more deeply tied to the geometry of spacetime itself rather than simple physical momentum. This distortion isn't just a curious detail. It reflects a much deeper truth about how rotation reshapes the very structure of space near a black hole. The geometry becomes more intricate, more layered, and considerably harder to describe using simple equations. Which is why, for rotating black holes, scientists rely on a different mathematical framework altogether, one known as the Kerr solution. The Kerr solution, named after the mathematician who first derived it, describes the space and time surrounding a rotating black hole with remarkable precision. It accounts not just for the mass of the black hole, but for its spin as well, capturing the way spacetime twists and curves in response to that rotation. Where the simpler, non-rotating case gives us clean spherical symmetry, the Kerr solution reveals a far more dynamic and layered structure, one with multiple boundaries, shifting geometries, and regions where the ordinary rules of space and time begin to blur together in genuinely strange ways. We won't dive too deeply into the mathematics tonight. That's not the purpose of this journey. But it's worth appreciating, even from a distance, that the humble idea of a black hole hides within it a surprising amount of structural richness. Some are still. Some spin. Some are modest in size. Others are almost incomprehensibly vast. Each one carves out its own unique boundary in space-time, shaped by its own particular history and characteristics. Now, here's a question worth sitting with for a moment. If black holes bend light so profoundly that nothing can escape from within their horizon, how do we know they're there at all? How do astronomers find something that, by its very nature, emits no light, and reflects none either? The answer lies not in looking directly at the black hole itself, but in observing its effect on everything around it. Black holes themselves are, in the truest sense, invisible. They emit no light. They reflect none either. If you were to look directly at empty space where a black hole resides, with nothing else nearby, you would see nothing. Simply darkness, indistinguishable from the emptiness of space itself. And yet, black holes are rarely, if ever, truly alone. They exist within galaxies, surrounded by gas, dust, and sometimes entire stars caught in gravitational dances that can stretch across centuries. It is through the behavior of this surrounding matter that astronomers are able to detect black holes at all. As gas and dust drift too close to a black hole, they don't simply fall straight in. Instead, they begin to spiral, drawn into a rotating structure known as an accretion disk. Picture, if you will, a great swirling ring of glowing material, circling faster and faster as it approaches the center, much like water spiraling around a drain, though on a scale, and with a violence, that dwarfs anything found on Earth. As this material spirals inward, it heats up dramatically. Friction between particles, combined with the immense gravitational forces at play, causes the gas to reach temperatures of millions of degrees. At such extreme temperatures, the material doesn't just glow, it radiates intensely across the spectrum, producing not only visible light, but X-rays and other high-energy radiation as well. It is this light, the light emitted by the superheated matter swirling around the black hole, that astronomers actually observe. The black hole itself remains hidden, wrapped in darkness. But the glowing disk surrounding it acts almost like a signature, a brilliant, telltale sign that something extraordinarily massive and dense lies hidden at its center. This is a subtle but important distinction to hold on to. When astronomers speak of observing a black hole, they are, in a very real sense, observing everything but the black hole itself. They are reading the story written in the swirling light around it, studying the motion of gas, the intensity of radiation, and the strange, telltale patterns that only make sense if something with tremendous gravity is lurking, unseen, at the very center of it all. And here's something particularly fascinating to consider. Matter doesn't simply plunge directly into a black hole the moment it gets close. Instead, it can spiral within that accretion disk for a remarkably long time, sometimes for what would amount to months, years, or even longer in Earth time, gradually losing energy, gradually drawing closer, before it ever reaches the event horizon itself. This means the accretion disk is not the same thing as the horizon. It's not as though matter suddenly vanishes the instant it enters this swirling structure. Far from it. The disk represents a long, gradual process, a slow spiral inward, governed by the loss of energy through friction and radiation, extending across a considerable region of space that lies well outside the event horizon itself. In fact, much of what astronomers observe when they study black holes comes from this outer region, from matter that is still, technically, free. Still outside the horizon. Still, in principle, capable of escape, even if the immense gravitational forces at play make that escape increasingly unlikely the closer it drifts toward the center. It's a bit like watching leaves caught in a slow, wide whirlpool, circling gradually closer to a drain, long before they ever reach the point of being pulled under. The drain itself, the true point of no return, lies further inward, hidden beneath the visible swirl of motion and light. This gradual inward spiral gives astronomers a remarkable window into the physics of black holes, even though the horizon itself remains forever unseen. By studying the light emitted from this inner disk, its brightness, its temperature, the way it flickers and shifts, scientists can infer an incredible amount about the black hole hidden at the center. Its mass, its spin, even, in certain cases, subtle hints about the warped geometry of space in its immediate vicinity. So although the event horizon itself can never be directly observed, no telescope, no instrument, however advanced, could ever capture an image of the horizon as a visible object. Its presence is written, quite clearly, in the behavior of everything that dares to venture close. As we continue moving forward together, we'll explore this inward spiral in even greater detail, following matter as it journeys closer and closer to the boundary we've spent this time coming to understand. We'll look at what happens to light as it bends and stretches near this region, and what subtle clues astronomers have gathered, across decades of careful observation, to confirm that these strange, invisible boundaries truly do exist, scattered throughout the universe. For now, let this image rest quietly in your mind, vast rings of glowing matter, swirling slowly through the darkness, circling a silence so complete that not even light can find its way back out. We ended with the image of glowing matter circling in the darkness. Let's stay with that image a little longer, because the closer this matter drifts toward the horizon, the more dramatic, and the more strange, its behavior becomes. As gas spirals inward through the accretion disk, it doesn't heat up gradually and evenly. The process intensifies the closer it gets to the black hole. Gravitational forces grow stronger. Friction between particles increases. And the material, compressed and agitated, begins to radiate with tremendous energy, long before it ever reaches the event horizon itself. This is part of why black holes, despite being invisible objects in their own right, can be surrounded by some of the brightest, most energetic light in the entire universe. It seems almost paradoxical at first. The very object responsible for this brilliant glow is itself completely dark. But the matter falling toward it, heated to extraordinary temperatures by the sheer intensity of the gravitational field, lights up the surrounding space in a way that can outshine entire galaxies. In the region just outside the horizon, this glowing material takes on particularly fascinating characteristics. As gas swirls within the innermost portions of the accretion disk, its emitted light doesn't reach us unchanged. It's altered, subtly and beautifully, by two remarkable effects: gravitational redshift and Doppler beaming. Gravitational redshift occurs because light, as it climbs outward from deep within a strong gravitational field, loses energy along the way. This causes its wavelength to stretch, shifting it toward the red end of the spectrum. It's a gentle reminder that light, even though it always travels at the same speed, is deeply affected by the shape of the space it's moving through, particularly when that space has been curved as dramatically as it is near a black hole. Doppler beaming, meanwhile, arises from the incredible speeds at which this material orbits. Matter in the innermost disk can move at a significant fraction of the speed of light, and at such velocities, the light it emits becomes concentrated, brightened, in the direction of motion. This means one side of the accretion disk, the side rotating toward us, can appear noticeably brighter than the side rotating away. A subtle but telling signature, one that helps astronomers piece together not just the presence of a black hole, but the direction and speed of the matter swirling around it. Now, this glowing disk doesn't extend infinitely close to the black hole. There's a natural limit, a point beyond which stable, circular orbits simply cease to exist. This boundary is known as the innermost stable circular orbit, often shortened to its initials, ISCO. Beyond the ISCO, matter can no longer maintain a steady, lasting orbit. Instead, it begins a final, rapid plunge toward the horizon, spiraling inward in a matter of moments rather than gradually drifting as it did further out. The ISCO, then, marks the true inner edge of the stable accretion disk, the last place where matter can still, in a sense, linger, before gravity takes hold completely and pulls it inward for good. Interestingly, the exact location of the ISCO isn't fixed. It depends heavily on the black hole's spin. For a black hole that isn't rotating, the ISCO sits at a certain, predictable distance from the horizon. But for a rapidly spinning black hole, the dragging of spacetime itself allows stable orbits to exist much closer in, shrinking the ISCO's radius considerably. In some extreme cases, matter can maintain a stable orbit almost right up against the horizon itself, a testament to just how profoundly rotation reshapes the space surrounding these objects. This inner region, right at the edge of stability, is far from calm. It's an environment defined by intense magnetic activity. Plasma, the superheated, electrically charged gas that makes up much of the accretion disk, becomes tangled in powerful magnetic fields as it swirls closer to the black hole. These fields twist, snap, and reconnect, releasing sudden bursts of energy in the form of flares. These flares don't occur randomly. Their timing is closely tied to the orbital period of matter at that specific distance from the black hole, meaning that by studying how quickly these flares flicker and repeat, astronomers can gain remarkable insight into just how close to the horizon this turbulent activity is actually taking place. In recent years, observations of a particularly famous black hole, known as M87*, located at the heart of a distant galaxy, have offered scientists a rare, evolving glimpse into this dynamic environment. Rather than remaining fixed and unchanging, the plasma and magnetic structures surrounding M87* appear to shift and evolve over time. Bright regions brighten. Structures rotate. Patterns that once seemed stable reveal themselves, upon closer and repeated observation, to be part of a slowly, continuously changing system. This has been a profound realization for astronomers, a reminder that even in a region shaped by some of the most extreme physics in the universe, nothing remains perfectly static. The environment surrounding a black hole is alive with motion, change, and energy, even though the black hole itself, hidden behind its horizon, remains forever silent and still. Perhaps one of the most visually striking consequences of this magnetic activity is the formation of jets. In certain black hole systems, powerful magnetic fields, combined with the dragging effect of rotating spacetime near the inner disk, can launch streams of particles outward, perpendicular to the accretion disk itself. These jets shoot outward from close to the horizon region at speeds approaching the speed of light, stretching, in some cases, for thousands of light years into intergalactic space. It's a remarkable contrast to imagine an object so gravitationally extreme that nothing can escape from within its horizon, and yet, from the region just outside that same horizon, some of the most energetic, fastest-moving particle streams in the known universe are being flung outward into the cosmos. Now, let's turn our attention to something even more delicate: the way light itself behaves as it passes near the horizon. Light doesn't travel in simple, straight lines near a black hole. As it passes through the intensely curved space surrounding the horizon, its path bends, sometimes gently, and sometimes so dramatically that light can find itself curving all the way around the black hole, again and again, before finally continuing onward. There's a very specific region where this effect becomes most extreme. Just outside the event horizon lies what's known as the photon sphere. Within this region, gravity is strong enough that light can, under the right conditions, enter into a temporary orbit, circling the black hole not once, but multiple times, before eventually escaping outward or spiraling further inward. This creates one of the most extraordinary visual phenomena in all of astrophysics. As light orbits the black hole within the photon sphere, some of it eventually escapes toward distant observers, but not before completing one, two, or even several loops around the black hole first. Each time light completes an additional loop before escaping, it contributes to a distinct, extremely faint ring of light, layered subtly on top of the others. These layered rings are known as photon rings, and they represent one of the most delicate and mathematically beautiful predictions in all of black hole physics. Each subring corresponds to light that has orbited the black hole a different number of times, the first subring representing light that made a single loop, the next representing two loops, and so on, each successive ring fainter and more tightly compressed than the last. What we perceive as the bright ring surrounding a black hole shadow, the glowing halo made famous by recent black hole imaging efforts, is, in truth, a superposition of all of this light that traveled directly to us, layered together with light that circled the black hole multiple times before finally breaking free. And here's a particularly delicate detail. This glowing ring isn't simply light created near the black hole. It's a distorted, warped image of the accretion disk itself. As light from the disk bends around the black hole, sometimes traveling behind it, sometimes below it, sometimes above it, all of these different vantage points become compressed together, from our perspective, into a single, thin, luminous ring encircling the darkness at the center. In other words, when we look at the glowing ring surrounding a black hole shadow, we aren't simply looking at one clear image of the disk. we're looking at multiple bent, stretched, and repeated reflections of that same disk, all layered together by the extraordinary curvature of space near the horizon, a kind of gravitational kaleidoscope, formed not by mirrors, but by the very geometry of space-time itself. It's a strange and beautiful thing to consider, that the glowing halo we've come to associate with black holes isn't a simple, direct image at all, but a delicate weaving together of light that has traveled some of the longest, strangest paths imaginable, circling again and again through curved space before finally reaching our eyes, or our telescopes, across the vast emptiness between the stars. As we move forward from here, we'll continue exploring this delicate interplay between light and gravity, venturing closer still to the horizon, to examine exactly what happens to space, time, and light in the final moments before everything, quite literally, disappears from view. For now, let this image linger gently in your mind, rings of light, bent and repeated, circling endlessly around a silence too complete for even light itself to escape. Let's return to that image of light bending endlessly around darkness, because there's more to uncover in how these delicate rings come to be, and what they truly represent. As we explored a moment ago, the glowing rings surrounding a black hole aren't simple, direct glimpses of light emitted near the horizon itself. They are, instead, distorted images of the accretion disk, light that has traveled circuitous, looping paths through curved space before finally reaching our eyes. It's worth sitting with this idea a little longer, because it reshapes something fundamental about how we should picture these glowing structures. When we look at these thin, bright rings, we aren't looking at a ring of light physically sitting near the horizon, the way a halo might sit around a candle flame. There is no glowing structure resting directly on the boundary of the black hole. Instead, what we're seeing is an optical effect, layered and repeated, formed by light from the disk being bent again and again as it passes through the warped space surrounding the black hole. Each ring is, in essence, a copy of the disk itself, stretched, curved, and folded by gravity into a shape our eyes interpret as a thin, glowing circle. This bending doesn't only create the rings we've already discussed. It also produces other, subtler distortions, visible arcs and humps of light appearing above and below the black hole, even in regions where, intuitively, you might not expect to see anything at all. Light originating from the far side of the accretion disk, the side directly behind the black hole from our point of view, can be bent so dramatically that it curves up and over, or down and under, the black hole itself, becoming visible to us as faint arcs positioned above or below the central shadow. It's a striking thing to consider, that some of the light reaching our telescopes hasn't traveled to us directly at all, but has instead looped around the back of the black hole first, bending through curved space in ways that allow us to see portions of the disk that would otherwise be completely hidden from view. In effect, gravity itself acts as a lens, gathering light from angles we would never expect, and folding it gently into our line of sight. Now, not every one of these looping light paths contributes equally to what we observe. As we touched on briefly before, each additional loop light makes around the black hole results in a progressively fainter contribution to the overall image. The first ring, formed by light that traveled to us with minimal bending, tends to be the brightest and most easily observed. But each successive ring, representing light that circled the black hole an additional time before escaping, grows dimmer and thinner, and increasingly difficult to detect. The reason for this fading comes down to simple probability. Each time light completes another loop around the black hole, only a small fraction of it manages to escape outward again. Most of that light, instead, continues to spiral inward, eventually crossing the event horizon and vanishing from the observable universe entirely. This means that with each additional orbit, the surviving population of photons shrinks considerably. Fewer and fewer manage to break free, resulting in rings that grow progressively fainter and more delicately thin the closer they sit to the black hole itself. It's a beautifully precise piece of physics, really. The rings aren't just decorative structures scattered around the black hole. They are, quite literally, a visual record of probability itself. A fading sequence of images, each one representing an ever smaller fraction of light that managed to survive its journey through some of the most extreme gravity in the universe. This layered structure of light naturally leads us to a broader, and perhaps more important distinction: the difference between the event horizon itself and what astronomers refer to as the black hole's shadow. It's easy, understandably, to assume that the dark region we see in black hole images is the event horizon, a direct visual representation of that boundary we've spent so much time exploring. But this isn't quite accurate. The dark region visible in these images, the shadow, is actually somewhat larger than the true event horizon. This happens because of the same gravitational lensing effects we've been discussing. Light that would otherwise pass safely by the black hole, missing the horizon entirely, can instead be bent so severely by the surrounding curved space that it becomes trapped, curving inward and eventually crossing the horizon, rather than continuing on its original path. This means that the region from which no light can escape to a distant observer, the region that appears dark to us, extends somewhat beyond the horizon itself. In other words, the shadow represents every direction from which light simply cannot reach us, whether because it originated from within the horizon, or because it was bent so dramatically by gravity that it was pulled inward before it ever had the chance to escape. It's a subtle but important distinction. The shadow isn't a direct image of the horizon. It's a slightly larger silhouette, shaped by the combined effects of the true boundary and the gravitational lensing that surrounds it. This is worth repeating gently, because it corrects a very common and understandable misconception. When people look at the now famous images of a black hole's shadow, glowing rings of light surrounding a dark central void, it's natural to assume that the edge of that darkness marks the precise location of the event horizon. But this isn't quite the case. The shadow and the horizon, while closely related, are not the same thing. The shadow is, in essence, a larger dark silhouette, cast not by the horizon directly, but by the combined effect of the horizon and the warped space immediately surrounding it. Light bending and light capture both contribute to this darkened region, extending its apparent size beyond the true boundary of the black hole itself. In fact, scientists have calculated this relationship with remarkable precision. The observable shadow, the dark region visible in these extraordinary images, is approximately twice the size of the actual event horizon. This is a striking figure, worth pausing on for a moment. When we look at these iconic images, the darkness we see stretching across the center isn't simply the horizon rendered visually. It's a region roughly double that size, shaped by the intricate interplay of gravity, light, and the surrounding curved geometry of space. This means that somewhere, nestled quietly within that visible dark circle, lies the true event horizon, smaller, more compact, and forever hidden from direct view, wrapped within the larger shadow cast by the bending of light around it. It's a gentle reminder of just how much interpretation, and how much careful physics, goes into understanding these remarkable images. The dark center that so captured the world's imagination, when the very first image of a black hole's shadow was released, wasn't simply a photograph of the horizon itself. It was, and remains, a photograph of something slightly different, slightly larger, a shadow cast by gravity, rather than a direct outline of the boundary we've spent so much of tonight coming to understand. As we continue forward together, we'll explore this relationship even further, examining precisely how scientists are able to distinguish between the shadow and the horizon, and what these subtle distinctions reveal about the mass, the spin, and the deeper nature of the black holes hidden quietly at the center of it all. For now, let this distinction settle softly into your thoughts, a boundary, small and hidden, wrapped gently within a larger shadow cast by the endless, patient bending of light through curved and silent space. We left off with the idea that the true event horizon lies hidden within a larger shadow, wrapped quietly in the bending of light around it. For a long time, that boundary existed only in equations, only in the careful mathematics of general relativity. But eventually, humanity found a way to catch a glimpse of it directly. On April 10, 2019, something remarkable happened. For the first time in history, an image was released showing the region immediately surrounding a black hole's event horizon. Not a simulation. Not an artist's rendering. An actual image, painstakingly assembled from data gathered by a global network of telescopes working together, all pointed toward the same distant target, separated by thousands of kilometers, yet synchronized with extraordinary precision. That image showed exactly what we've been describing, a glowing, asymmetric ring of light, brighter on one side than the other, encircling a dark central shadow. It was the black hole at the heart of the galaxy M87, sitting some 55 million light-years away, and yet, through years of careful observation and analysis, scientists were able to bring its shadow into focus for the very first time. The significance of this moment extended far beyond simply capturing a striking photograph. This image served as a profound confirmation of Einstein's theory of general relativity, not in the gentle, everyday gravity we experience here on Earth, but in the most extreme gravitational environment imaginable. For over a century, general relativity had predicted the existence of black holes, had predicted their shadows, their photon rings, the exact way light should bend around them. And now, finally, observation had caught up with theory, confirming, with striking precision, that these predictions held true even in the most extreme conditions the universe has to offer. It's worth pausing here, just for a moment, to appreciate the scale of that achievement. A theory conceived in the early 20th century, built from elegant mathematics and careful reasoning about the nature of space and time, had been tested against one of the most violent, most extreme environments in the entire cosmos, and it had passed that test beautifully. Now, let's return to something we touched on briefly earlier, because it deserves a closer, more careful look, the way light itself is transformed as it travels near a black hole. We mentioned before that one side of the glowing accretion disk often appears brighter than the other. This effect, known as Doppler beaming, occurs because matter within the disk moves at tremendous speeds, sometimes reaching a significant fraction of the speed of light itself. When something moves that quickly toward an observer, the light it emits becomes concentrated, and correspondingly brighter, in the direction of that motion. This means that the side of the disk rotating toward us appears distinctly brighter, and notably, its light shifts toward the blue end of the spectrum. This happens for much the same reason a sound wave shifts to a higher pitch as its source approaches you, except here, instead of sound, we're speaking of light itself, compressed and intensified by extreme velocity. Meanwhile, the opposite side of the disk, the side rotating away from us, tells a very different story. Its light appears dimmer, and shifts toward the red end of the spectrum, growing fainter and warmer in tone, much like a sound fading and dropping in pitch as its source moves away. This contrast between the bright, blue-shifted side, and the dim, red-shifted side, creates the distinctive asymmetry we see in real black hole images, an asymmetry that tells scientists a great deal about the speed and the direction of the material spiraling ever closer toward the horizon. But speed isn't the only factor reshaping light near a black hole. Gravity itself plays an equally profound role. As we touched on earlier, light climbing outward from deep within a strong gravitational field loses energy along the way, stretching its wavelength and shifting it toward red. This effect, known as gravitational redshift, becomes increasingly severe the closer light originates to the event horizon. Light emitted just outside the photon sphere experiences a noticeable redshift. But light emitted from even closer, right at the very threshold of the horizon itself, experiences a redshift so extreme that it becomes stretched almost beyond recognition, its energy drained away by the sheer intensity of the gravitational field it's struggling to escape. And there's something even stranger happening here too, something involving not just the color of light, but the very passage of time itself. Light emitted extremely close to the horizon doesn't just lose energy on its way out. It can also be profoundly delayed, taking an extraordinarily long time to reach distant observers, far longer than you might expect based on distance alone. This phenomenon has a name. It's known as gravitational time delay, or sometimes, the Shapiro delay, named after the physicist who first predicted and later confirmed this effect. In essence, strong gravity doesn't just bend the path light takes. It also stretches the time that path requires. Signals sent from deep within a strong gravitational field, particularly from regions near a black hole's horizon, take significantly longer to reach a distant observer than they would if that same signal had traveled the same distance through flat, empty space. Gravity, in other words, doesn't just curve space. It curves time as well, weaving the two together into something scientists refer to as space-time, a single, unified fabric where distance and duration become deeply, inseparably intertwined. This idea leads us gently into one of the most beautiful, and most genuinely mind-bending, aspects of black hole physics, the fact that falling toward a black hole looks entirely different, depending on who is doing the watching. Imagine, for a moment, an object, perhaps a small probe, or a scattering of dust and debris, slowly drifting toward the event horizon. Now imagine two very different observers, each watching this same event unfold, from two very different vantage points. The first observer watches from a great distance, safely far away from the black hole's immense gravity. From this distant perspective, something remarkable, and rather counterintuitive, begins to happen as the object approaches the horizon. Rather than watching it cross the boundary and disappear, the distant observer sees the object slow down. Gradually, at first. But then, more and more dramatically, the closer it gets to the horizon. At the same time, the light coming from that object grows increasingly redshifted, its color shifting further and further toward the red end of the spectrum, and beyond, eventually fading into wavelengths too long, too faint, to detect at all. Here's the truly strange part. From this distant vantage point, the object never actually appears to cross the horizon. Instead, it seems to slow, and fade, and slow further still, approaching the boundary asymptotically, always drawing closer, yet, from this outside perspective, never quite arriving. Its image lingers, frozen in a sense, growing fainter and fainter, stretched by gravitational redshift, until it fades entirely beyond the ability of any instrument to detect. This isn't simply an illusion, or a limitation of our telescopes. It emerges directly from the extreme time dilation, and the profound gravitational redshift that occurs near the event horizon. To a distant observer, every signal sent by that falling object, every flicker of light, every pulse of radiation, takes progressively longer to climb back out of the deepening gravitational well. The signals grow weaker. They grow more delayed. And they stretch out across what would appear, to that outside observer, to be an almost infinite span of time. So in a very real sense, from far away, nothing ever truly appears to fall into a black hole at all. It simply fades, slowly, gently, redshifting into darkness, its final moments stretched out across a duration that, from the outside, seems to have no clear end. It's a strange, almost dreamlike way to think about falling into a black hole. Not a dramatic, sudden disappearance, but a slow, gradual fading, as if the object were being gently absorbed into the silence of the universe itself, rather than abruptly erased from it. As we continue forward from here, we'll explore the other side of this remarkable story, what the experience of falling might actually feel like from the perspective of the object itself, rather than from the perspective of a distant, patient observer watching quietly from afar. We'll discover that these two perspectives, though describing the very same event, tell two remarkably different stories, each equally true, each shaped by the deep, inseparable connection between gravity, light, and time itself. For now, let this image rest gently in your mind, a distant light, fading slowly into red, drawing ever closer to a boundary it seems, from far away, destined never quite to reach. We ended with an image of light fading slowly into red, a distant object seeming, from far away, to approach the horizon but never quite arrive. Now, let's shift our vantage point entirely, and ask what this same journey might feel like from the perspective of the object itself, rather than from someone watching safely from a distance. This is where the story of the event horizon becomes truly strange, and, in its own way, quietly beautiful. Because the two perspectives we've been exploring, the outside view and the inside view, don't just differ slightly. They differ profoundly, describing what feels almost like two entirely separate realities, even though both are describing the very same event. For the object actually falling toward the horizon, whether that object is a scattering of dust, a spacecraft, or, in the realm of thought experiment, an astronaut, the experience of crossing the boundary is, in many cases, remarkably uneventful. There is no wall to strike, no sudden barrier to push against, no dramatic flash of light, or violent jolt, marking the moment of crossing. This might come as a surprise, especially if you've pictured the event horizon as some kind of dramatic threshold, a line drawn sharply across space, waiting to be crossed with great consequence. But for a sufficiently large black hole, particularly one many times more massive than our Sun, a falling observer would simply continue falling, smoothly and continuously, without any local sign, any immediate signal, that they had just passed a point from which there could be no return. This is one of the more elegant, and admittedly counterintuitive, features of general relativity. In the standard picture, the region right at the horizon is not marked by any dramatic curvature, any violent tearing of space, or any physical singularity. Space-time there can remain smooth, gentle, even, in a purely local sense. If you were the one falling, and you looked only at your immediate surroundings, at the space directly around you, you might notice nothing unusual at all in that particular moment. No boundary to see. No wall to feel. Simply the continuation of your fall, uninterrupted, into deeper and deeper gravity. Of course, this doesn't mean the experience is without consequence. Far from it, as we'll explore in a moment. But the crossing of the horizon itself, that precise, mathematically defined threshold we've spent so much time discussing, does not announce itself locally. There's no signpost. No shimmer. No felt sensation of finality. And here's the truly haunting part of this story. Once that crossing occurs, there is no way for the falling object to send word of it back to the outside universe. No signal, no light, no whisper of information can climb back out across that boundary. This means that outside observers, no matter how advanced their instruments, no matter how long they wait, can never receive direct confirmation of the moment someone, or something, crosses the horizon. From the outside, as we explored before, the object simply fades, redshifting slowly into darkness. From the inside, the crossing happens quietly, without ceremony, marking a threshold that only the object itself will ever truly experience, and can never report back. Two perspectives. One event. And yet, in a very real sense, two entirely different stories, each equally valid, each shaped by the deep, inseparable relationship between gravity, light, and the passage of time itself. Now, let's turn our attention to something we touched on briefly, several segments ago, the strange and fascinating behavior of rotating black holes. We spoke earlier of frame dragging, the way a spinning black hole doesn't just rotate in place, but actually drags the surrounding fabric of space-time along with it, sweeping space itself into motion. Near the horizon of such a black hole, this effect becomes so powerful that it creates a truly remarkable region, one unlike anything found around a non-rotating black hole. This region is known as the ergosphere, and within it, the dragging of space becomes so extreme that nothing, not matter, not even light itself, can remain still relative to a distant observer. Everything within the ergosphere is forced to co-rotate with the black hole, swept along by the sheer momentum of twisting space-time, whether it wants to or not. What makes the ergosphere particularly fascinating is a peculiar and rather beautiful consequence of this extreme rotation. Within this region, it becomes theoretically possible for particles to possess what physicists call negative energy, relative to a distant, stationary observer far away. This is a deeply strange concept, one that defies our everyday intuition about what energy even means. And yet, within the powerful, twisting geometry of the ergosphere, it becomes mathematically, and theoretically, possible. This strange property opens the door to a genuinely remarkable idea, first proposed by the physicist Roger Penrose, and now known as the Penrose process. In principle, if a particle were to split into two within the ergosphere, with one fragment falling into the black hole carrying negative energy, the other fragment could escape outward carrying more energy than the original particle possessed before it ever entered the region. In doing so, energy would effectively be extracted from the black hole's own rotation, siphoned away and delivered back out into the universe. It's a wonderfully strange thought, isn't it, that a rotating black hole, an object defined by its inescapable gravity, might also, under very particular and delicate conditions, serve as a source of usable energy, drawn not from matter falling in, but from the spinning of space-time itself. Let's turn now to something a little more visceral, the powerful, and sometimes violent, tidal forces that exist near a black hole's horizon. You may have heard the term spaghettification before, and while it certainly sounds playful, even whimsical, it describes something genuinely dramatic. As an object falls toward a black hole, it doesn't experience gravity's pull uniformly across its entire length. Instead, the part of the object closer to the black hole feels a noticeably stronger gravitational pull than the part farther away. This difference in pull, this gradient of force stretching across the object, is known as a tidal force. Near smaller black holes, particularly those only a few times more massive than our Sun, this tidal effect can become extraordinarily intense, even before reaching the horizon. The difference in gravitational pull between one end of an object and the other can become so severe that the object is stretched, elongated, pulled apart along its length, while simultaneously being compressed from the sides, hence the vivid, almost playful image of spaghettification, a term that, despite its lightness, describes a process that would be swift, and thorough, and entirely unsurvivable. But here's where the story takes an unexpected, and rather counterintuitive turn. You might assume that larger black holes, being more massive and more gravitationally powerful overall, would produce even more extreme tidal forces near their horizons. But the opposite is actually true. For extremely massive black holes, particularly the supermassive black holes found at the centers of galaxies, tidal forces at the horizon can actually be remarkably gentle, mild, even, compared to the violent stretching experienced near smaller black holes. This happens because the size of the horizon itself grows so large, for these supermassive objects, that the difference in gravitational pull across even a considerable distance, say, the length of a spacecraft, or a human body, becomes relatively small. In other words, a black hole containing the mass of billions of suns might allow an object to cross its event horizon with barely any noticeable stretching or compression at all, at least, not yet. The true, violent tidal forces, in such cases, wait until much deeper within the black hole, closer to the singularity itself. Which brings us, gently, to one final and important distinction: the difference between the event horizon and the singularity that lies hidden far beyond it. Throughout our journey so far, we've focused almost entirely on the horizon, that quiet, invisible boundary marking the edge of no return. But the horizon is not the center of a black hole. It is not the point where all of the black hole's mass is concentrated. It is simply a boundary, a threshold, wrapped around something far stranger and far more extreme, lying deeper still within. That true center, the singularity, lies significantly deeper inside the black hole than the horizon itself. It represents a place where, according to our current understanding of physics, the curvature of spacetime becomes so extreme that our equations, our models, our very ability to describe what's happening, begins to break down entirely. The horizon, then, is best understood not as the heart of the black hole, but as its outer boundary, a quiet, softly defined threshold, wrapped protectively, in a sense, around a mystery that lies considerably deeper within, one that we have not yet fully come to understand. As we continue our journey from here, we'll begin moving deeper still, exploring what lies beyond the horizon, what theoretical physics suggests about the singularity itself, and what remains, even now, among the most profound and unresolved mysteries in all of modern science. For now, let this thought settle gently in your mind, that the boundary we've spent so much time exploring is not an ending in itself, but a threshold, a quiet doorway, wrapped around depths far stranger and far more distant than the horizon alone could ever reveal. We closed the last chapter of our journey with the idea that the horizon is not an ending, but a threshold, a doorway wrapped around depths still stranger. Let's step through that doorway now, gently, and consider what lies beyond it. According to general relativity, deep within the black hole, far past the boundary of the event horizon, lies a place unlike anything else predicted by physics. This place is known as the singularity, and it represents the true heart of the black hole. It's here, in this innermost region, that all of the black hole's mass is thought to be concentrated, compressed into a space so small and so extreme that our current understanding of physics simply ceases to function. It's worth being clear about something important here. The singularity is not the horizon. It is not the boundary we've spent so much time exploring throughout this journey. It lies considerably deeper, hidden well beyond that outer threshold, tucked away where no light, no signal, and, as far as we understand, no information of any kind can ever escape to reveal its secrets. General relativity, the very theory that predicts the existence of black holes in the first place, also predicts this singularity as an unavoidable consequence of its own mathematics. Wherever a sufficient amount of mass becomes concentrated within a small enough space, the equations of general relativity suggest that spacetime curvature grows without limit, eventually becoming, in the strictest mathematical sense, infinite. It's at this point that classical physics, the elegant, well-tested framework that has served us so well in describing gravity, motion, and the shape of the universe simply breaks down. The equations no longer provide meaningful answers. And most physicists agree that this breakdown is not a flaw in reality itself, but rather a signal, a clear indication that some deeper theory, one that successfully merges gravity with quantum mechanics, will eventually be needed to describe what truly happens in that innermost region. In the simplest possible model of a black hole, one that isn't spinning and carries no electric charge, this singularity exists at a single, precise mathematical point, often labeled, quite simply, as r equals 0, a shorthand way of describing a location at the very center, where the radius of the black hole's interior geometry shrinks down to nothing at all. It's a strange and almost poetic image, if you allow yourself to sit with it for a moment. All the mass, all the gravitational influence, everything that once made up a collapsing star or a dense cloud of matter, compressed down to what current theory describes as an infinitesimally small point, a place of infinite density, and, at least mathematically, infinite curvature. This singularity, then, is the true extreme heart of the black hole, standing in sharp contrast to the horizon itself, which, as we discussed at length earlier, remains, in most cases, remarkably smooth and unremarkable from a local perspective. And this brings us to a subtle but genuinely important point of clarification, one that took physicists some time to fully understand and untangle. In some of the earliest mathematical descriptions of black holes, the equations appeared to suggest that something dramatic, even catastrophic, was happening right at the horizon itself, as if the horizon, too, might represent some kind of singular, breaking point in space-time. For years, this created genuine confusion, and even some debate, within the physics community. But eventually, through more careful mathematical analysis, scientists came to realize that this apparent breakdown at the horizon wasn't a real, physical problem at all. It was, instead, what's known as a coordinate artifact, a kind of mathematical illusion, arising not from anything genuinely catastrophic happening in spacetime itself, but from the particular choice of coordinates being used to describe it. This is a bit like describing the surface of the Earth using a flat map. Near certain points, particularly near the poles, common map projections can distort distances and directions dramatically, sometimes even suggesting strange, seemingly impossible behavior, purely because of how the three-dimensional surface of a sphere has been forced onto a flat, two-dimensional representation. The Earth itself isn't doing anything strange near the poles. The map simply struggles to represent that region accurately. Something remarkably similar happens with the standard coordinates originally used to describe black holes. These coordinates, while perfectly useful for describing regions far from the horizon, begin to behave poorly, mathematically speaking, as they approach that boundary, creating an illusion of extreme, even infinite, values, purely as an artifact of the coordinate system itself, not because spacetime is actually doing anything dramatic in that particular location. To resolve this confusion, physicists eventually developed alternative coordinate systems, better suited to describing the region near, and even beyond, the horizon. One of the most well-known of these is called the Kruskal-Szekeres coordinate system, named after the physicists who developed it. Using this more carefully constructed mathematical framework, scientists were able to demonstrate clearly that the horizon itself is not a true curvature singularity. Spacetime, when viewed through this more appropriate lens, remains smooth and well-behaved at the horizon, just as our earlier discussion suggested it would feel to a falling observer passing through that boundary. This distinction matters a great deal. It confirms, with mathematical rigor, that the horizon and the singularity are two genuinely different things. One, a smooth, geometrically defined threshold, and the other, a place of true, extreme breakdown, hidden much deeper within. Now, let's shift our attention once more, this time toward the practical question of how scientists actually go about testing and confirming the existence of these remarkable horizons in the first place. Long before the historic image of a black hole's shadow was ever captured, astronomers had already gathered compelling, if indirect, evidence pointing toward the existence of event horizons. Some of this evidence came from a particularly clever line of investigation, involving the careful comparison of different types of dense, collapsed astronomical objects. In the earliest days of X-ray astronomy, researchers began studying a category of objects known as black hole candidates, dense, compact objects believed, based on their mass and behavior, to likely be black holes, though direct confirmation remained elusive. To help verify these suspicions, scientists compared these candidates against a very useful point of reference: neutron stars. Neutron stars, much like black holes, form from the collapsed remains of massive stars. But unlike black holes, neutron stars possess an actual, physical surface. Matter falling onto a neutron star doesn't simply vanish beyond an invisible boundary. It strikes that solid surface directly, releasing a burst of additional energy upon impact, energy that black holes, lacking any such surface, should not produce in quite the same way. This distinction became a delicate observational proving ground. In their comparisons, researchers made a fascinating discovery: black hole candidates were consistently, noticeably dimmer, particularly in X-ray emissions, than similar systems containing neutron stars. This dimness made a great deal of sense. If these candidates truly did possess event horizons, rather than solid surfaces. Without a physical surface to strike, matter falling toward a suspected black hole wouldn't produce that additional burst of impact energy seen so clearly in neutron star systems. Instead, it would simply continue falling, silently crossing the horizon, taking whatever remaining energy it carried along with it, into a region from which no further signal could ever return. This subtle but consistent difference in brightness became one of the earliest, and most persuasive, pieces of indirect evidence supporting the existence of true event horizons, a quiet confirmation, written not in a dramatic image, but in the careful comparison of light, and its curious, telling absence. Alongside this evidence, astronomers also turned their attention to something more detailed still: the precise shape and subtle distortions found within X-ray light emitted by matter swirling in the innermost regions of accretion disks, very close to the horizon itself. Normally, when a particular element emits X-rays, it does so at very precise, well-defined wavelengths, creating what scientists call a spectral line, a sharp, narrow feature that can be measured with great precision. But when this same emission occurs very close to a black hole, deep within its intense gravitational field, and amid the extreme orbital speeds found in the inner disk, something remarkable happens to that once narrow spectral line. Instead of appearing sharp and well-defined, the line becomes noticeably broadened, and often skewed, stretched unevenly toward both higher and lower energies. This distortion arises from precisely the effects we've discussed throughout our journey together: gravitational redshift, stretching the light toward lower energies as it climbs outward from deep within the gravitational well, combined with Doppler effects, arising from the tremendous orbital speeds of the emitting material, blue shifting light from matter moving toward us, while red shifting light from matter moving away. By carefully studying the exact shape of these broadened, skewed spectral lines, astronomers have been able to extract remarkably detailed information about the black holes producing them, including, quite precisely, their rate of spin, and the intensity of relativistic effects occurring in that innermost, most extreme region of space. It is, in many ways, one of the most elegant confirmations of everything we've discussed so far, written not in a single, breathtaking image, but in the quiet, careful shape of light itself, subtly bent and reshaped by the extraordinary gravity of the horizon it once passed so closely by. As we move forward from here, we'll continue exploring this careful, patient process of discovery, following the long trail of evidence that has, piece by piece, over decades of careful observation, confirmed the reality of these remarkable, invisible boundaries scattered throughout our universe. For now, let this thought rest quietly in your mind: a boundary, smooth and unremarkable to those who cross it, yet wrapped around a mystery so profound that even the light passing near it carries quiet, subtle evidence of its presence. This confirms the facts are accurate. Good. Now I can narrate with confidence. We left off with the idea that light passing near the horizon carries quiet, subtle evidence of its presence. But light isn't the only messenger capable of revealing these hidden boundaries. In more recent years, scientists have discovered an entirely different way of listening to black holes, not through light at all, but through ripples in the fabric of space-time itself. These ripples are known as gravitational waves, and they're produced under some of the most violent, most energetic circumstances imaginable, specifically, when two black holes spiral inward toward one another, drawing closer and closer over great spans of time, before finally colliding and merging into one. As this dramatic spiral unfolds, and as the two black holes finally merge, the surrounding space-time doesn't remain calm and undisturbed. It ripples outward, carrying with it a wealth of information about the extreme, strong field region existing just outside each black hole's horizon. For years, gravitational wave observatories have been capturing the echoes of these distant, cataclysmic events. But recently, researchers achieved something new, something that brought this field of study remarkably close to the horizon itself. In new gravitational wave research, scientists reported detecting what they described as fingerprints of an event horizon, drawn directly from the data of a black hole merger. This wasn't simply another detection among many. It represented a genuinely new way of probing the region closest to a horizon that had ever been studied using gravitational waves. The breakthrough came from analyzing something called the direct wave, the very final burst of gravitational ripples, emitted in the last fleeting moments immediately following a black hole merger. By carefully isolating this particular signal from the surrounding noise, researchers were able to extract details about the newly formed black hole's horizon with a level of precision that had never before been achieved through this method. Among the most striking findings to emerge from this work was evidence of frame dragging, that same twisting of spacetime we discussed earlier, occurring near the horizon of a rotating black hole. Detecting this effect wasn't simply confirmation of something long predicted by theory. It marked the first time this particular signature had been drawn directly out of gravitational wave data, offering a genuinely new observational window into a phenomenon that, until recently, had only been described mathematically. This remarkable evidence emerged from the study of a particular gravitational wave event, one known by the designation GW250114, the strongest, most powerful gravitational wave signal ever recorded, detected by the LIGO Observatory in January of 2025. Within the data from this singular, extraordinary event, researchers found a signal rich enough and clear enough to reveal details about the horizon region that had never before been accessible through any observational method. What makes this line of research particularly exciting, looking forward, is what it might eventually make possible. Researchers involved in this work have suggested that this method, refined and developed further, may one day allow scientists to search for something extraordinarily subtle, tiny quantum fluctuations, occurring right at the edge of the horizon itself. This would represent an entirely new frontier, bridging the elegant, large-scale predictions of general relativity with the strange, probabilistic world of quantum mechanics, in a region of the universe uniquely suited to studying both at once. This growing body of research reflects something significant happening across the broader field of black hole physics. Scientists are increasingly turning their attention toward the horizon region itself, driven by a growing understanding that this seemingly quiet, unremarkable boundary may, in fact, contain subtle signatures, delicate traces of information, observable from outside the black hole, that could offer profound insight into the deeper physics governing these extraordinary objects. Now, let's turn our attention to something even stranger still, a place where general relativity and quantum mechanics meet directly, giving rise to one of the most puzzling and actively debated ideas in all of modern physics. This phenomenon is known as Hawking radiation, named after the physicist who first proposed it. At its core, Hawking radiation is a quantum effect, deeply and inseparably tied to the existence of event horizons themselves. It emerges from a subtle, almost paradoxical interplay between quantum mechanics and the extreme curvature of spacetime found near a black hole's boundary. According to this theory, radiation can actually be produced just outside the event horizon, arising not from matter falling into the black hole, but from the strange behavior of quantum fields in the presence of such extreme gravity. In the framework of quantum mechanics, empty space isn't ever truly empty. It's filled, instead, with fleeting pairs of particles, constantly appearing and disappearing in tiny, fleeting fluctuations. Near a black hole's horizon, this delicate quantum dance can be disrupted in a peculiar way, occasionally allowing one particle from such a pair to escape outward as radiation, while its counterpart falls inward, across the horizon, and is lost forever. This process introduces something deeply strange into our understanding of black holes, the idea that they might not be entirely black after all, but might instead radiate, ever so faintly, releasing a slow, gentle trickle of energy back out into the universe. But this elegant idea carries with it a deeply unsettling consequence, one that has occupied physicists for decades. It involves a subtle but profound connection known as quantum entanglement, existing across the boundary of the horizon itself. In quantum mechanics, entangled particles remain deeply linked, no matter the distance separating them, in ways that defy our everyday intuition about separateness and locality. Near a black hole's horizon, the particle pairs responsible for Hawking radiation become entangled precisely in this way, one particle escaping outward, its partner disappearing forever beyond the horizon. This entanglement lies at the very heart of what's become known as the black hole information paradox, a genuinely unresolved puzzle, one that sits right at the delicate, unsettled boundary between general relativity and quantum mechanics. It raises a deeply challenging question. If information about everything that ever fell into a black hole is truly lost forever, swallowed beyond a horizon from which nothing can return, this seems to directly conflict with one of the most fundamental principles in all of quantum mechanics, the idea that information, in a deep and technical sense, can never truly be destroyed. It's a puzzle that remains, even now, among the most actively studied, and most deeply debated, mysteries in all of modern theoretical physics. As we continue forward from here, drawing ever closer to the conclusion of our long journey together, we'll explore this mystery a little further, considering what physicists have proposed, and what still remains unknown, about the delicate, quiet boundary that has occupied our attention throughout this entire exploration. For now, let this thought settle gently in your mind, a boundary, faintly glowing with the softest whisper of radiation, entangled invisibly with a mystery that reaches into the deepest, most unresolved corners of physics itself. We ended with the entanglement of light and mystery, a boundary reaching into the deepest, most unresolved corners of physics. Let's continue drawing closer to that edge, because there is still more to explore in this quiet, unsettled frontier where our best theories begin to falter. Throughout our journey together, we've treated the event horizon largely as a prediction of general relativity, a smooth, geometrically defined boundary, elegant in its simplicity, even amid the extraordinary physics surrounding it. But many physicists now view the horizon as something more than simply a fascinating astrophysical feature. They see it as a genuine testing ground, a natural laboratory, written into the fabric of the cosmos itself, where our understanding of gravity may begin to break down, and where the strange, probabilistic rules of quantum mechanics may start to take precedence. This idea sits at the very edge of modern physics. General relativity, for all its elegance, describes gravity as a smooth, continuous curvature of space-time. Quantum mechanics, meanwhile, describes the universe in terms of discrete particles, probabilities, and strange, fleeting fluctuations. These two frameworks have been remarkably successful, each within its own domain. And yet, they have never been fully, seamlessly unified into a single, coherent theory. The event horizon, many physicists suspect, may be precisely the place where this tension becomes unavoidable. Very close to the horizon, in that innermost, most extreme region of curved space, quantum effects are expected to become significant in ways that classical gravity, alone, simply cannot describe. It's here, at this delicate threshold, that some of the deepest, most persistent questions in modern physics quietly converge. Several intriguing, and still highly theoretical, ideas have emerged from this line of thinking. Some models predict that near-horizon quantum fluctuations could give rise to entirely new kinds of structures that would replace the smooth, simple horizon we've described throughout much of our journey with something considerably more intricate. One such proposal imagines what are known as fuzzballs. Rather than a black hole possessing a true singularity, hidden deep within a smooth, empty interior, fuzzball models suggest that the entire structure of a black hole might instead be composed of an incredibly dense, tangled configuration of quantum strings, extending all the way out to what we would normally consider the horizon itself. In this view, there is no true empty void beneath the boundary. The fuzz, in a sense, extends right up to the very edge. Another proposal, similarly strange, and similarly controversial, suggests the possible existence of what physicists call a firewall. In certain theoretical models, attempting to resolve some of the deep paradoxes surrounding information and entanglement near the horizon leads to the unsettling suggestion that an object falling toward a black hole might encounter, not a smooth, uneventful crossing, as we described earlier, but instead an intensely energetic barrier, a firewall, of sorts, right at the threshold of the horizon. It's worth being clear that these remain speculative, deeply theoretical proposals, still very much debated within the physics community, rather than confirmed features of black holes as we currently understand them. But they illustrate something important, just how strange, and how genuinely unresolved, our understanding of the horizon becomes, once quantum effects are taken seriously in this extreme environment. This leads us gently into a broader set of ideas, ones that reach even further beyond the boundaries of Einstein's original theory. One particularly elegant proposal suggests that the event horizon might behave, in some deep sense, like a kind of quantum phase transition, similar, conceptually, to the way water transitions into ice, or into steam, under changing conditions. In this view, the horizon wouldn't simply be a passive geometric boundary, but rather a genuine physical transition, marking a fundamental change in the underlying quantum state of spacetime itself. This perspective offers an intriguing possible resolution to some of the deep paradoxes we've touched on throughout our journey. In this view, many of the strange, seemingly contradictory properties associated with horizons, the information paradox, the tension between smoothness and firewalls, may not represent fundamental flaws in physics itself, but rather, the natural, expected consequence of extending classical physics, built for gentler, more moderate conditions, too far into a regime where quantum effects can no longer be reasonably ignored. It's a humbling thought, when you consider it carefully. Perhaps the horizon isn't paradoxical at all, in any deep, fundamental sense. Perhaps it simply marks the point where our current tools, remarkably successful as they've been, quietly reach the edge of their usefulness, giving way to a deeper, not yet fully understood theory waiting patiently beyond. This search for a deeper understanding has led physicists to explore a wide range of theoretical alternatives to general relativity itself, each offering its own unique perspective on what might truly be happening near, and within, a black hole's horizon. Some of these alternative models predict something genuinely remarkable, the possibility of non-singular black holes. Rather than harboring a true singularity at their core, a place where curvature becomes infinite and physics breaks down entirely, these models suggest that some deeper, more complete theory of gravity might smooth that extreme point out altogether, replacing it with something finite and considerably less mathematically troublesome. Other proposals, often referred to collectively as modified gravity models, suggest that the fundamental rules governing gravity itself might differ, ever so slightly, from what general relativity predicts, particularly in the most extreme environments found near a black hole's horizon. If true, this could subtly change the way light bends as it passes close to these objects, altering the precise, delicate paths that give rise to the photon rings and shadows we explored earlier in our journey together. This possibility opens up a genuinely exciting avenue for future observation. If modified gravity models are correct, even slightly, the appearance of photon rings and shadows, those delicate, nested structures of light we discussed at length, might differ in subtle, measurable ways from what standard general relativity predicts. This means that, as our observational tools continue to improve, growing ever more precise and sensitive, scientists may eventually be able to distinguish between these competing theoretical possibilities, simply by studying the fine, delicate details hidden within the light surrounding a black hole's shadow. Other researchers have taken this exploration even further, considering the intriguing possibility of extra-spatial dimensions, beyond the familiar three we experience in everyday life. In certain theoretical frameworks, additional hidden dimensions, curled up at scales far too small for us to directly perceive, could subtly influence the behavior of gravity near extremely dense objects like black holes. Studying black holes, in this context, becomes a way of searching for subtle deviations from ordinary, expected behavior, deviations that might, just possibly, offer indirect evidence for the existence of dimensions beyond the ones we can directly observe or move through. And throughout all of these diverse, wide-ranging theoretical explorations, one particular idea continues to reappear, again and again, as a central, unifying thread. Hawking radiation. Despite the many different, sometimes dramatically diverging models physicists have proposed for what might lie beyond general relativity, Hawking radiation remains a key, foundational process across a great many of these alternative frameworks. Whether a black hole harbors a true singularity, or something smoother and more exotic in its place, whether gravity behaves exactly as Einstein predicted, or diverges subtly in extreme conditions, the quiet, persistent trickle of radiation, emerging gently from just outside the horizon, continues to play a central, unifying role in nearly every serious attempt to understand what black holes truly are, at the deepest level. It's a remarkable thing, when you step back and consider it. A concept originally proposed as a delicate bridge between gravity and quantum mechanics has become something of a common thread, weaving its way through a wide, diverse landscape of otherwise very different theoretical ideas, a quiet reminder that despite so much uncertainty, so much that still remains unknown, there are certain deep, persistent truths that continue to anchor our understanding, even amid the most speculative and unresolved corners of modern physics. As we draw ever closer to the end of our long journey together, we'll begin gathering these many threads, weaving together everything we've explored, from the quiet elegance of the horizon's geometry, to the strange, layered rings of light, to the deep, unresolved mysteries reaching into the quantum realm itself. For now, let this thought rest gently in your mind, a boundary, simple in its geometry, yet hiding within it, perhaps, one of the deepest and most beautiful unresolved mysteries in the entire universe. We ended with the thought that this simple boundary may hide one of the deepest, most beautiful mysteries in the universe. As we come to this final stretch of our long journey together, let's linger a little longer at that quantum frontier, exploring the subtle, measurable ways this hidden mystery might one day reveal itself. One of the more compelling aspects of these theoretical horizon models is that, even though the interior of a black hole remains, and likely will always remain, permanently hidden from view, several of these models predict effects that could be measured from outside, subtle, exterior signatures, observable without ever needing to cross the horizon itself. This is, in many ways, a hopeful thread running through even the strangest and most speculative corners of black hole physics. Even if the deepest truths remain forever concealed, their influence, their quiet fingerprints, may still ripple outward, into regions we can observe. Consider, for a moment, the photon rings and shadows we explored earlier in our journey, those delicate, nested structures of light, formed by photons looping again and again around a black hole before finally escaping. Some theoretical models suggest that near-horizon quantum fluctuations, tiny, fleeting distortions in the fabric of spacetime itself, could become large enough to subtly distort these structures. If true, this means that the shadow and photon ring we observe might not be a perfectly clean, purely classical prediction, but could carry within it, subtly woven into its structure, faint traces of quantum behavior occurring right at the threshold of the horizon. This same quantum turbulence, if it exists, might not stop at merely reshaping the visual appearance of the shadow. It could also, according to some models, disrupt the delicate flow of matter within the accretion disk itself, particularly in that innermost region, closest to the horizon, where gravity grows most extreme, and where the usual, gentle spiral of infalling gas might instead become subtly perturbed by these underlying quantum effects. There's another particularly delicate possibility worth considering here as well. If these near-horizon quantum couplings are strong enough, light passing extremely close to a black hole might exhibit something resembling scintillation, a kind of subtle flickering or shimmering, not unlike the twinkling we observe in starlight as it passes through Earth's turbulent atmosphere, though here, the turbulence wouldn't come from air, but from the quantum fabric of spacetime itself, gently perturbed near the horizon's edge. It's a beautifully strange thought, isn't it, the possibility that light, having already traveled such an extraordinary journey, bending and looping through the most extreme gravity in the universe, might carry with it one final, subtle signature, a faint shimmer, encoding within it whispers of quantum behavior occurring at the very boundary it once passed so closely by. These same theoretical quantum effects could extend even further, reaching into an entirely different form of cosmic messenger, gravitational waves. We spoke earlier of how these ripples in spacetime, produced during the inspiral and eventual merger of black holes, carry with them detailed information about the strong field regions surrounding each horizon. Some models now suggest that if near-horizon quantum effects are significant enough, they could subtly alter the pattern of gravitational waves emitted during this in-spiral process, introducing delicate deviations from what pure, classical general relativity alone would predict. This opens up yet another fascinating possibility for future observation. As gravitational wave detectors continue growing more sensitive, more precise, scientists may eventually be able to search for these subtle deviations directly within the data itself, searching, quite literally, for the whispered signature of quantum gravity, hidden gently within the ripples of merging black holes. Now, let's turn our attention to something a little more unusual still, a fascinating theoretical thought experiment involving quantum matter, brought deliberately close to a black hole's horizon. Imagine, if you will, a quantum gas, an incredibly cold, delicately structured collection of particles, governed by the strange, probabilistic rules of quantum mechanics, slowly lowered, closer and closer, toward the horizon of a black hole. According to certain theoretical models, something remarkable begins to happen to this gas as it approaches that extreme boundary. Despite existing, quite normally, in three-dimensional space, the gas begins to behave as though it were effectively confined to only 2 dimensions. This peculiar effect arises from the extraordinary curvature of spacetime near the horizon, which subtly reshapes the way particles within the gas can move and interact with one another. It's a strange, almost dreamlike transformation, matter, ordinary in every other respect, gradually losing access to one of its familiar spatial dimensions, simply by drawing close enough to this extreme gravitational boundary. Alongside this dimensional transformation, another curious thermodynamic effect emerges as well. Within this same near-horizon setup, the pressure exerted by the quantum gas becomes highly anisotropic, meaning, quite simply, that the pressure is no longer the same in every direction. Near ordinary conditions, gas exerts pressure uniformly, equally, in all directions at once. But near a black hole's horizon, this uniformity breaks down. Pressure along the direction pointing toward the black hole differs dramatically from pressure in directions running parallel to the horizon itself, a subtle but profound reflection of just how deeply the extreme geometry of spacetime reshapes even the most basic thermodynamic properties of matter. This leads us to a broader, and quite important, technical point, one that underlies much of this final, quantum-focused stretch of our journey. When matter is brought extremely close to a black hole's horizon, physicists can no longer rely on one of the simplifying assumptions that makes many calculations in this field considerably more manageable, the assumption of a fixed background spacetime, one that remains essentially unaffected by the presence of the matter being studied within it. Very close to the horizon, this simplifying assumption begins to break down. The matter itself, however small or seemingly insignificant, begins to influence the very geometry of spacetime surrounding it, an effect known as back reaction. This means that, in these extreme near-horizon calculations, physicists must account for a kind of feedback loop, matter shaping spacetime, even as spacetime, in turn, continues to shape the behavior of that very same matter. It's an intricate, deeply interconnected relationship, one that becomes impossible to ignore the closer we look toward the horizon's edge. And finally, let's turn to a particularly delicate and profound question, one that draws together many of the deepest themes we've explored throughout our entire journey. What happens to quantum properties themselves, as they draw near, and interact with, the extreme environment of a black hole's horizon. We spoke earlier of Hawking radiation, and of decoherence, a related quantum effect, in which delicate quantum properties gradually lose their distinctly quantum character, blurring instead into something closer to ordinary, classical behavior. Near a black hole's horizon, both of these effects can act to weaken certain quantum properties, disrupting the delicate coherence and correlations that define quantum systems under gentler, more ordinary conditions. And yet, remarkably, recent studies suggest that these effects, while genuinely disruptive, do not necessarily destroy these quantum properties completely. Instead, quantum entanglement, coherence, and something known as mutual information, subtle measures of how deeply connected different parts of a quantum system remain, have been found to evolve in genuinely unusual, and not yet fully understood, ways, shaped by the combined influence of the Hawking effect, and the deeply curved spacetime surrounding the horizon itself. This is, perhaps, one of the most fitting notes on which to bring our long, patient journey to its close. Even here, at the very edge of what physics currently understands, amid the strange, disorienting interplay of quantum mechanics and extreme gravity, something delicate, something deeply connected, continues to persist, reshaped, weakened perhaps, but not entirely erased. And so, we arrive, gently, at the end of this long exploration together. Over these many hours, we've traveled from the simplest, most elegant definition of the event horizon, a boundary where escape becomes impossible, all the way to the furthest edges of theoretical physics, where quantum mechanics and gravity intertwine in ways we are only just beginning to understand. We've watched matter spiral slowly inward through glowing accretion disks, its light bent and layered into delicate, nested rings. We've considered two entirely different perspectives on falling toward the horizon, one, from far away, watching an object fade slowly into an endless, stretching red. The other, from within, where the crossing itself unfolds quietly, without ceremony, without any dramatic sign of finality. We've explored the strange, twisting physics of rotation, the profound confirmation offered by that first, historic image, and the delicate, whispered evidence now emerging from the ripples of merging black holes themselves. And we've drawn, finally, to the very edge of the unknown, to fuzzballs, and firewalls, to quantum phase transitions, and to the deep, unresolved mystery of information, entanglement, and coherence, all quietly persisting, in some form, near the boundary of the darkest objects in our universe. The event horizon, we've come to understand, is not simply an ending. It is a threshold, a quiet, patient boundary, wrapped around mysteries both ancient and impossibly new. It is a place where light bends beyond recognition, where time stretches gently into what looks, from far away, like forever, and where some of the deepest, most fundamental questions in all of physics continue, quietly, patiently, to wait for answers still to come. Wherever you are now, however far into rest or stillness this long journey has carried you, let this final image settle gently into your mind, a distant boundary, dark and silent, wrapped in rings of bent and gentle light, holding within it, still, some of the universe's oldest and most beautiful, unanswered questions. Rest now, gently, beneath that quiet, distant dark.